Hi everyone, I'm Isiki from FKE UTHM. Today we'll be looking at some exercise on capacitor. At the end of this video, we are going to solve this question which is related to the parallel plate capacitor. So let's look at these questions. Okay, so in these questions, we have to find out what is the capacitance, okay, of each of the capacitor as shown in the figure above. So we have a capacitor A and also the capacitor B. Okay, we will do it one by one. So let's focus on capacitor A first. So for capacitor A, you can see this is the terminal of the capacitors. So this is the parallel plate. Okay, I want to highlight the parallel plate. Okay, so if the terminal is connected to a DC source, okay, one of the parallel plate will be positively charged and the other parallel plate will be negatively charged. Okay, so you can see electric field, okay, in between these two plates. Okay, so in between these two plates, we have two dielectric mediums. So the first one with the epsilon R1 equals to 4, and the second one is epsilon R2 equal to 6. So let's look at or recall back what is the formulas that we use to find the capacitors, okay, of a parallel plate capacitor. Okay, so this is the equation that we have to use to determine the capacitance of a parallel plate capacitor. Okay, so I explained before, this one represents the dielectric medium between the two parallel plates, and this one represents the surface area. Okay, this is the surface area, and this one represents the separations or the distance, okay, between two parallel plates. Okay, so here we have the distance. Okay, so the distance here is, if we follow the figure B, okay, same things. Okay, the distance over here would be D, yeah. Okay, the distance, okay, is D. Okay, 5 millimeters. Okay, so this equation is derived when we have a capacitors that has a uniform, okay, I would say that we have a uniform dielectric medium. Okay, uniform dielectric mediums is that it means that, okay, in between two parallel plates, okay, you have only one type of dielectric material. Okay, so you look at this capacitor A. Okay, so this capacitor A has two dielectric mediums. Okay, R1 and also R2, two mediums. Okay, so we could see this thing is like two capacitors. Okay, so one capacitor is over here. Okay, the other capacitor is over here. Okay, we can say that there are two capacitors. Okay, so when we have two capacitors, when we want to find the total capacitance, okay, we have to identify whether they are parallel capacitors or they are series capacitors. Okay, what is the meaning of parallel? Parallel, it means that capacitor, so you have a capacitor. Okay, you have capacitors. You have capacitors. Okay, so this is a parallel. Okay, so you know that it is a parallel capacitance. Okay, capacitor, when you found that you have to split the I, okay, to two junctions. Okay, so this is the parallel capacitance. Okay, for the series, okay, series is easy. You just have a two capacitor arranged next to each other, so the same total of I is passing through both capacitors. So this one is a series configurations. Okay, so how to determine whether this configuration is series or parallel? Okay, so here we are looking at the electric field directions. Okay, so we know the electric field will be from positive plate to the negative plate. Okay, so if you look at this case, the electric field, it has a choice, okay, whether to go to the left side or to go to the right side. That means that you have an electric field, it's like breaking into two regions, right? So for this case, okay, our capacitor is in the parallel configurations. Okay, parallel configuration. So to get the total capacitance, okay, Okay, for parallel configuration, we have to take the C1 plus the C2. Okay, so C1 plus the C2. So what is C1? Okay, C1 would be, okay, let me write down the C total is equal to C. You have epsilon R1. Okay, you have the X1, which is area of the capacitor 1. Okay, and the distance of capacitor 1 plus epsilon R2. Okay, for the S2 area capacitor number 2 and distance capacitor number 2. Okay, to be precise, I think I will use epsilon 1 and epsilon 2. Okay, epsilon 1 equals to epsilon naught multiply epsilon R1. Okay, epsilon 2 represent epsilon naught multiply epsilon R2. So this is the same thing like when we are doing the boundary conditions. Okay, so let's do this. Okay, so epsilon 1 equals to epsilon naught, okay, multiply with epsilon R1. So in this case, the epsilon R1 is 4, okay, and multiply with X1. So S1 represents the area. So we look at the area given by the questions. So for the whole plate, okay, for the whole parallel plate, so the whole parallel plate, it is 30 centimeter square. Since capacitor 1 only occupied half of it, so the area is half of it. Okay, so we say that the area is 15 centimeter square, and the separation between two plates, okay, is D. So D is 5 millimeter. So 5 millimeter. Okay, and for the second capacitor, we have epsilon naught and epsilon R2. Okay, is 6. So we have 6, and this one is also 15 centimeter square and 5 millimeter. Okay, so if you look at these calculations, you can see that, okay, the unit is different. Okay, this is centimeter and this is millimeter. Okay, it's not the same, so you have to convert all to meter. Okay, convert all to meter. Okay, convert all to meter. So to convert this 15 centimeter square, okay, we will do like this. Okay, so 15 it will remain, okay, times 10 power negative 2. Okay, so this negative 2 stands for centi, and because you have a square here, so you have to square this centimeter. And for the distance, so this is 5 times 10 power negative 3. Okay, so this one is the same like this. Okay, 6. So you have 15 multiply 10 negative 2 and then power 2. Okay, so 5 times 10 negative 3. So if you could not understand, why this one you have to power with 2, okay, you can think about this. Okay, let's say this one is the area of the capacitor. Okay, it is 15, right? So here it can be 5 centimeter, and here you can assume it to be 3 centimeter. So when you find the area, okay, so the area will be 15 centimeter square. Okay, 5 times 3. Okay, so if you convert both of it to be meter, so it would be 0.05 meter. Okay, and this is 0.03 meter. So if you use a calculator to calculate this thing, right? So it's 0.05 times 0.03. So you will have 1.5. Okay, 1.5, we'll say that times 10 power negative 3 meter. This one is the area. So this one is the area. Look at how you get this thing. Okay, so if you apply this formula, right? So
the answer is 15 times 10 power negative 4. Okay, so when you put this in front, okay, it is times 10 power negative 3. Okay, which is the same thing like when you do the area calculation in the unit of meter. Okay, so that's why we have to do this. Okay, in the exam, if you cannot remember, you can use this concept to convert back. Okay, so now you have all these value replaced. You can calculate the answer, and if you see this, you actually could factor it. Okay, so you have epsilon naught, okay, and then you have 15 times 10 power negative 4, and you have 5 millimeter times 10 power negative 3. Okay, and you have this 4 plus 6, which is 10. So you can factor it first before you do the calculations. So it is 10 multiplied 4 multiply 15 minus 4, okay, and divide 5 minus 3. Okay, so the answer is 2.65, okay, times 10 power negative 11 farad. Okay, so this is the capacitance. Okay, for these capacitors, okay, so this one is a parallel configurations. Parallel configurations. So now we look at the capacitor B. Capacitor B. So this capacitor B has two terminals as well. Okay, you can see this is a terminal. One will be positive terminal and one will be negative terminal. So the electric field, okay, will penetrate two material. There is no option for this electric field. It must penetrate two material. So this concept is the same like when you arrange a capacitor in series. Okay, so you can see that this I has no option. Okay, it must pass through both capacitors. So for this one, we call it as a series configurations. Series configurations. And the capacitance, okay, the total capacitance for this series configuration would be 1 over C. T equals 1 over C1 plus 1 over C2. Okay, so this is the equation. So we will apply these equations. Okay, so look at the separations. So the separation is half. Okay, just now is fully. Okay, is 5 millimeter. Now is half. And the area is 30 centimeter square. Complete. Okay, complete. Okay, so we go to capacitor B. So for capacitor B, okay, we'll be using this equation. This is the general equations, okay, for capacitors. So we have 1 over CT equals to 1 over C1. Okay, 1 over C1 is equals to, I would say that D1 over epsilon 1 S1. Because it's 1 over C. Okay, so plus this D2 over epsilon 2 S2. Okay, so the separations is 5 millimeter just now. So if we split it into half, so it is 2.5. Okay, so 2.5 millimeter. So I will say that millimeter. And epsilon naught, epsilon R1 equals to 2. And the area is 30 centimeter. Okay, so this one I'm going to convert it into meter square. Okay, and plus the D2 is 2.5 millimeter. Okay, and epsilon naught. Okay, then we have 6. Then we have this is multiply and 30 times 10 power negative 2 and power 2. Okay, so you can calculate the answer. So this one you can take it out also. So we take out the 2.5 on 2.5. No, we cannot take like this. Okay, let's calculate this one. So this is 4.71 multiply them power 10 and plus, so here we have so this is 1.557 times 10 power 10. So we add them together. So it's equals to 6.28 times 10 power 10. Okay, so this is not your final answer. You must remember, you are looking for the CT. Okay, so the answer that you get just now is 1 over CT. Okay, so to get the CT, you have to do this. Okay, 1 over this. Okay, so you have 6.28. So the answer is 1.59, okay, times 10 power negative 11 farad. Sorry class, here there is something wrong, okay, on the number here. It should be 4 instead of 2, so I will correct it. So this is 4. So we have to calculate back again. What will be the value? So let me calculate. So this is 2.35 times 10 power 10. Okay, so this is 3.92. Okay. 10, positive 10. Okay. So the answer is 2.55 times 10 power negative 11. So this is the capacitance. For the capacitors, okay, in the question B.